Hi everyone, welcome back to chemistry. A while back we talked about the different states of matter, but I did want to do a little bit of a review. So remember that a gas is a state of matter where atoms and molecules are moving freely. And the reason for that free movement is that they've been given lots and lots of energy. So if you look at the gas over here, if you were to zoom in on this gas really, really close, you would see all of these little particles kind of moving around at these really fast paces in this container, just kind of colliding with each other and with the sides of the container like this, right? So they've got lots and lots of energy, and so they'll fill up the volume of whatever container they're in. And of course, if you added a lot of heat here to your container here, there's a chance that you would add enough that would give these particles enough energy, and the cork would actually pop off of this container. Liquids have a little less energy, but enough to kind of keep them changing positions relative to each other. A lot of times chemists will describe it as like these atoms can kind of slide past each other in the liquid. So they're in constant contact, but they can kind of move relative to one another because they have enough energy to change positions. Whereas a solid, that's when atoms and molecules, they don't really have enough energy to move. They're constantly in contact, right? They're like touching each other, right? And they're in fixed positions relative to one another, but they don't have enough energy to move like something like a gas or a liquid does. So they're kind of stuck in this fixed position. We also talked about phase changes a little bit. So we talked about, the going from a gas to a liquid is condensation, right? Going from the other way, liquid to gas, is evaporation. We said, you can freeze your liquid and that turns it into a solid, or you can melt your solid and that'll turn it into a liquid. And then we said these are probably new to us. You can actually go directly from a solid to a gas and skip the liquid phase altogether, and that's called sublimation. And we can do that in lab with different technology. Or you can go from a gas to a solid, straight to a solid, right, without passing through the liquid phase, and we call that deposition. Just a review on that. Some terms that are not review, some terms that are new to us, is endothermic or exothermic. So if heat is added to a substance, that process is endothermic. Endothermic. In this instance, right, heat is increasing the speed of the molecules, causing them to move faster. If heat is removed from a substance, the process is exothermic. And in this instance, heat is decreasing the speed of the molecules and causing them to move slower. And this releases heat to the surroundings. You can also think of endothermic as requiring heat. So if, let me get back to yellow here. If endothermic processes require heat, right, you're putting in some heat as something that you're putting into your substance, then exothermic is the opposite. It releases heat. Okay, I like to think of it as exit or as exo like exit. So on the left there, you've got a picture of an endothermic process, something like ice melting. So when ice melts, we've got to have some kind of input of heat to cause that ice to melt, right? So say you put that ice outside on a hot day, that heat from outside is going to be added into your system, your ice cube system, and that's an endothermic process, and it requires heat, right, to melt those ice cubes. And then the opposite of that is something like fire burning, right? That's an exothermic process. We know, right, if we touch fire, it's gonna burn us, right? That's because that fire is releasing heat to the surroundings. So these terms, endothermic and exothermic, I do want you to memorize. I want you to know what endothermic is and what exothermic is. Thinking about phase changes a little bit more, you probably have seen this kind of graph before if you've already finished our water lab in our class. If you're watching this in a future quarter, it's possible we haven't gotten to the water lab just yet, so stay tuned. But this is a phase diagram specifically for water. Okay, and on the x-axis, we have heat being added. Okay, so on the x-axis, that's our heat being added. And on the y-axis is our temperature. Okay, so as we add more and more heat, our temperature will raise, right? On the y-axis. All right, so this can be a little bit weird looking at first, but let's break it down a little bit. So you'll notice we have these kind of diagonal lines here that I'm highlighting in yellow. And then we have these kind of like plateaus that I'm highlighting in blue on our graph. So before I've added any heat, I'm in the solid state as water. So I probably look like this ice cube here. Okay. And that's what this diagonal line is referring to. I'm in this kind of solid state. As I'm adding more and more heat going right on the x-axis, my temperature is also going to raise. So I'm going to get this kind of diagonal line happening, right? Which is showing as I'm adding that heat, I'm also raising my temperature. And as I raise my temperature, right, there's going to be a point at which I hit a temperature where I start going from a solid to a liquid. And for water, right, that temperature is 0 degrees Celsius. Right, that's the melting point of water. That's when we're going to go from solid to liquid, or melt our ice. So at that point, at 0 degrees Celsius, I've started to melt my ice. But I haven't yet added quite enough energy to change all of my molecules from a solid to a liquid. So I'm still moving on the x-axis, still adding more energy. But as I'm adding that energy, some of that energy is getting absorbed by some of the molecules and allowing them to melt and turn into liquid, to go into the liquid state. And some of our molecules haven't quite gotten there yet, right? We haven't added enough energy to get all of those molecules into the liquid state yet. So that's why you see this kind of plateau. All right, but then there comes a point, right, when we start, we have allowed all of our solid water to turn into to liquid water, and we can keep adding heat, keep adding heat, keep adding heat, keep adding heat, until I get to this other point. And at that point here, that's when some of my water molecules are going to start turning into, from liquid to gas, right? I've added enough heat to some of these molecules to get them to go into the gaseous phase. Okay, and that happens at what temperature? Yeah, 100 degrees, right? The boiling point of water, right? So there's a melting point, right, where we go from solid, oops, I don't know why it's doing that, where we go from solid to liquid. And then there's a boiling point where we go from liquid to gas, right? Okay, so at that point, right, I've added enough heat to get some of my, I'm starting to get some of my molecules going from the liquid to the gas. And I'm going to keep adding heat until all of those molecules are able to get into the gas phase. And once they are, right, they've turned into a gas. And now they're on this line here, this diagonal line. And they've all turned into a gas. All right, so the diagonal lines that I had in yellow there, right, those are when our water is at a different phase. So the first diagonal line, we have water in a solid phase, the second one's in the liquid phase, and the third one's in the gaseous phase. And then for our plateaus, those are our phase changes. So let's take a note of that. Phase changes. That's when those phase changes are occurring. Either from liquid to solid to liquid or from liquid to gas. So just to recap, the melting point is the temperature at which the substance goes from solid to liquid. Boiling point is the temperature at which the substance goes from liquid to gas. At a substance's melting point or boiling point, these two phases can actually exist and do exist simultaneously. That's what those plateaus are. Remember, right? We haven't added enough energy to get all of our molecules into the liquid phase here. So at our plateau, we would say we're in the solid and the liquid phase, right? And same idea up here, right? We haven't added enough energy to get all of our molecules into the gaseous phase. So we got some liquid and some gas, right? That's what we see as boiling. And then just our final recap, the temperature of a substance does not change as the substance goes from one phase to another. We see this graphically, right? That's where those plateaus are. It's weird, right? We're adding more heat, but that heat is going directly into the molecules to get them to go from one phase to another, and it's not changing the overall temperature. It's being used up by changing the state. All right, so for each of these phase changes of a substance, there's a characteristic quantity of heat that's needed to perform the phase change per gram or per mole of that material. So for instance, with water, right? When we look at something like the ocean, and ocean water is not pure water, right? But just kind of bear with me for a second. For something as vast as the ocean, it's going to take a lot of heat energy to raise that water's temperature by even just a small amount. But it's not going to take as much heat energy to raise the temperature of just, a liter of water. That's not going to take as much heat energy. Just like when you're boiling water, right? If you're boiling a giant pot of water for lots of pasta, that's going to take a lot more heat energy that you have to add in from your stove than if you were just boiling just a little bit of water for a cup of tea or something. And we can actually calculate the amount of heat per gram or mole that's required for these phase changes. And one of the ways we can do that is using something called the heat of fusion. So the heat of fusion is represented as delta H with the subscript fusion, FUS, is the amount of heat per gram or per mole that's required for a phase change at the melting point. Or another way of thinking about it is it's the amount of heat energy required to melt 1 gram of a substance, or 1 mole, depending on what your heat of fusion is trying to represent, right? The heat energy required to melt 1 gram of your substance, or is it the amount of heat required to melt 1 mole of your substance? All right, and that is actually given by these nice equations. So if you're looking at something like with your mass, right, or you measured something in grams, and you want to know how much heat is required to get that to go from a solid to a liquid, right, to melt it, then you're going to use this heat of fusion equation that I've circled. If you have moles, then you're going to use the other one, right? We all know it's the same idea, right? It's just that in the right equation, we have moles times our delta H FUS, and on the left, we have mass times our delta H FUS. And again, you don't need to memorize these equations. They'll be given to you on an exam. You just need to know how to use them. Now, if the heat of fusion describes the amount of heat per gram or mole that's required for a phase change that occurs at the melting point, then the heat of vaporization is the amount of heat per gram or per mole required for a phase change occurring at the boiling point. Right? So we talked about, right, the heat of fusion, right, going from a solid to a liquid. And now I want to talk about the heat of vaporization, which is going from a liquid to a gas, right? How much heat is required? How much heat energy do I need to add to get my substance from the liquid phase to the gaseous phase? And that's given by these equations here. You'll notice they look almost identical to the equations, and let me zoom out a little bit here, for heat of fusion. And that's because it's the same equation. We're just using different variables here to represent the different things we're looking for, but it's the same mathematical operation. So these equations, right, you've got one, again, for the mass, if you have your mass given in grams, and you've got one for moles, if you've got your moles of your substance. All right, now, if you were looking at this and you were like, oh my God, how are we going to get this delta H vap or delta H FUS fusion, right? How are we going to get that crazy looking thing here? Well, that's actually always given to you on a chart. So I will give you the some kind of chart like this, and it's your job to say, okay, well, what substance do I have? What substance do I have? And what's the heat of fusion or the heat of vaporization? And then plug those accordingly into your equation. So let's try this out. So we'll start with the heat of fusion. And I've written my equation up there already. So this one says, how much heat is necessary to melt 55.8 grams of ice at 0 degrees Celsius? The heat of fusion of water is 79.9 calories per gram. So in this case, right, again, we were given the heat of fusion. I'll color code that in yellow. We were given that in our problem here, 79.9 calories per gram. So let's just make a list of what we're given here. We have our delta HFUS, and that equals 79.9 calories per gram, little c calories. And then we have our mass too, which is what? Yeah, 55.8 grams. Right, we've got that here. All right, so now it's just a matter of plugging it into this equation. So it looks a lot scarier than I think it is. So we've got 55. Actually, let me write the equation down here again, just so it's pretty clear here what we're doing. So heat equals our mass, which is 55.8 grams, times our delta H fusion, or our heat of fusion, which is 79.9 calories per gram. And then we can calculate that. So 55.8 times 79.9 is going to give us 4,458.42. And then let's figure out our units, and then we'll round for sig figs. So this is what the calculator spit out. It looks like we have grams on the top here and grams on the bottom here. So what can we do with those? Yeah, let's cancel them out. And then we're left with calories. I don't see anything else that's going to cancel with those calories. So we're going to write our calories here. And that is great because we're looking for the amount of heat required to change this amount of my substance from solid to liquid. Okay, and it's going to require, right, a unit related to heat, which is calories. Okay. And let's go ahead and round to, what do you think, 3 sig figs? So this one's a little bit tricky for sig figs. So you'll notice, right, this has quite a few sig figs. I want to get to this spot here. So I got to look over here, and I'm going to say, okay, well, looks like that's 5 or greater. So I'm going to round up. So that's going to give me 4, 4, 6. And then don't forget your 0 there. Okay, you don't want to just write 4, 4, 6. 4, 4, 6 is not anywhere near 400 or 4,400. Okay, that is not similar. You're not representing the same value anymore. Okay, we want to round, but we still want to be in the ballpark of our answer, right? 4,460 is a good rounded number for 4,458.42. And it still has 3 sig figs. Why isn't this 0 a sig fig? Yeah, no decimal point, so it's not significant. All right, let's try this other one for heat of vaporization. So this one was for heat of fusion. Let me actually write that. Heat of fusion example. And let's do heat of vaporization example. All right, so this one says, how much heat is necessary to vaporize 685 grams of water at 100 degrees Celsius? The heat of vaporization of water is 540 calories per gram. Now, I want to mention too, I meant to mention it before, it's giving you this information here, the temperature. And that's not necessarily to trick you, but it's just to kind of remind you that at 100 degrees Celsius, that is when your water is going to start to vaporize, right? So don't be fooled and think, hey, that means it's a delta T, right? I have a temperature there, so I need my M times C times delta T. No, this is actually just kind of another, it's kind of redundant. It's just saying, hey, when I'm trying to vaporize this thing at 100 degrees Celsius, how much heat is necessary. Okay, same idea here, right? It tells you that you're at 0 degrees Celsius. Well, you're at 0 degrees Celsius because you're trying to melt your ice, right? You're at 0 degrees Celsius and you want to know, hey, how much heat is necessary to melt all of this ice? Okay, I don't know if that made sense, but hopefully if you have any questions, let me know as always. So we need our equation. So heat equals M times this time H delta H vap, or vaporization, rather than fusion. All right, so let's copy this down here just so we have it here to work with. And then let's just see what we have. What are we given in the problem? Well, looks like I have my mass, right? And that's 685 grams of water. And then my heat of vaporization is also given to me, and that's 540 calories per gram. Okay, so I can actually plug these in. So let's go ahead and, I don't know, we'll color code these a little bit. So my mass times my HVAP, that's going to give me 685 grams, leaving your units in there, right? Times 540 calories per gram. All right, so 685 times 540 is going to give us, ooh, big number, 369900. And let's take a look at these units here. Looks like our grams are going to cancel out, right? And we're going to be left with calories, which is great because those are a unit of heat. And then we want to round to, looks like 3 sig figs again. So we want to get to this digit here. So for this one, again, kind of tricky. I would go to 370,000 calories. So 370,000 calories. That's what I would round this to. So I looked at this number here and I said, well, if I look to the next door neighbor, that's definitely greater than 5. So we got to round up. But when I round that 9 up, that's going to force me to round this 6 up to 7 as well. So we'll have 370,000 calories there as our final answer. And again, right, this only has 3 sig figs.